Every year, human beings discard billions of tons of PET plastic. It is a highly durable material designed to last, which means these mountains of waste will sit perfectly intact in our environment for centuries. The comforting narrative is that we can just recycle our way out of this. But traditional recycling is actually downcycling. The process melts the original plastic down, weakening its chemical bonds to create lower-grade materials like polyester fibers or cheap packaging. Through this industrial pipeline, the physical mass of the plastic is never actually destroyed. It is simply chopped up, melted, and reshaped into a less useful form. Our current infrastructure does not eliminate the plastic problem. It only hits the snooze button, briefly delaying the material's inevitable journey to the landfill. In a completely different sector, modern engineering is heavily reliant on quantum dots. These are highly valuable light-emitting nanoparticles that allow us to manipulate light with submicroscopic precision. Because of their incredible ability to absorb and emit light, quantum dots drive massive global industries. They are the core components required to harvest solar energy and to manufacture advanced consumer displays. But producing them carries a severe hidden cost. Manufacturing traditional quantum dots relies heavily on toxic heavy metals like cadmium and lead. Our pursuit of high-efficiency, next-generation technology is actively generating a dangerous, parallel environmental hazard. Recently, researchers found a way to collide these two problems into a single solution, synthesizing clean, highly valuable carbon quantum dots directly from plastic trash. The process begins by taking shredded PET plastic and subjecting it to an acid-catalyzed cleavage at 150 degrees Celsius. The acid bath violently tears apart the long, durable polymer chains of the plastic. Next comes a process called heteroatom doping. While the carbon structures are broken apart, researchers introduce specific non-carbon atoms into the mixture, like nitrogen or sulfur. The entire mixture is then baked at 280 degrees Celsius. This extreme heat forces the fractured plastic to rebuild itself, permanently locking those new atoms into its framework. This electron microscope image shows the result. The chaotic waste has organized into highly graphitic, perfectly spherical nanoparticles, measuring just 3.6 nanometers across. By tearing the material down to its atomic base and forcing it to rebuild, the researchers have completely erased the plastic's original identity. It is an entirely new, highly functional material. These newly formed dots have a distinct baseline capability. When exposed to UV light, they fluoresce with a brilliant, intense glow. This creates a unique on-off-on mechanism. If iron is present in a water sample, it binds directly to the dot, instantly turning the light off. But if fluoride is introduced, it aggressively reacts with the iron, stripping it away and immediately restoring the light. This microscopic chemical reaction translates into a highly sensitive, dual-mode alarm system. We can use the exact same batch of dots to test water supplies for two entirely different, invisible pollutants. The very material that originally clogged our rivers and oceans is now the exact instrument we use to ensure that water is safe. Most fluorescent materials share a common, frustrating limitation called aggregation-induced quenching. If you dry them out to use in solid electronics, the particles clump together and permanently lose their ability to glow. But these PET-derived dots bypass that completely. They maintain a vibrant, highly stable fluorescence, even when reduced to a dry, solid state. We can also engage in color modulation. By simply tweaking the recipe of nitrogen or sulfur during the initial acid bath, chemists can permanently dictate the exact color the final solid powder will emit. This dry state stability solves a massive manufacturing hurdle. It gives engineers the exact physical properties they need to build customizable solid-state optoelectronics and next-generation consumer displays without relying on toxic heavy metals. Mastering this atomic alchemy shifts how we look at global pollution. We now have the ability to harvest mountains of discarded plastic as a renewable resource for high-tech manufacturing.